Have you ever tracked a flight from Los Angeles to Tokyo and wondered why it swings dramatically northward, passing over the frozen wilderness of Alaska instead of cutting straight across the Pacific? This puzzling route has left countless travelers scratching their heads, watching their flight tracker draw what appears to be an absurdly inefficient path across their screens. You might think airlines are wasting fuel, adding unnecessary hours to your journey, or perhaps following some obscure regulatory requirement. But here's the surprising truth: that seemingly bizarre detour is actually the fastest, most fuel-efficient path between these two cities. What you're witnessing isn't a mistake or a compromise, it's a brilliant demonstration of how our planet's geometry works. The culprit behind this confusion isn't airline planning, but rather the flat maps we've relied on for centuries, which have quietly distorted our understanding of global geography. When flat maps lie to us, every world map hanging in classrooms, printed in or displayed on our screens, shares a fundamental flaw. They attempt to represent a three-dimensional sphere on a two-dimensional surface. This mathematical impossibility forces cartographers to make compromises, and these compromises have shaped how billions of people perceive our world. The most famous example, the Mercator projection, created in 1569, brilliantly preserves shapes and angles, making it invaluable for maritime navigation. However, this projection dramatically inflates the size of landmasses near the poles while compressing equatorial regions. Greenland appears nearly the size of Africa on a Mercator map, when in reality, Africa is 14 times larger. These distortions don't just affect how we perceive land sizes, they fundamentally warp our intuition about distances and the shortest paths between locations. What looks like a straight line on your flat map often represents a significantly longer journey in three-dimensional reality. The elegant mathematics of great circles. Imagine stretching a rubber band between two pins on a globe. The band naturally forms the shortest possible path between those points, creating what mathematicians call a great circle route. These routes don't follow lines of latitude or longitude, which are simply human constructs drawn on maps for reference. Instead, they trace unique arcs that minimize the actual distance traveled through three-dimensional space, cutting through the sphere's surface in the most efficient way possible. This principle has guided navigators for centuries, from ancient Polynesian wayfinders crossing the Pacific to modern airline dispatchers planning today's flights. When you fly from New York to Beijing, your aircraft follows a great circle route that sweeps dramatically northward, sometimes passing within a few hundred miles of the North Pole. On a flat map, this looks absurd, like taking a detour through Canada and Russia, when you could obviously fly straight west. But on our spherical planet, that northern arc actually saves hundreds of miles and cuts flight time by nearly an hour. Earth's imperfect shape changes everything. Our planet holds another secret that affects flight planning. Earth isn't actually a perfect sphere. Due to its rotation, centrifugal forces have caused our world to bulge slightly at the equator, creating what geoscientists call an oblate spheroid. The difference might seem trivial. Diameter exceeds the polar diameter by approximately 42 kilometers, or about 26 miles, but this variation has significant implications for long-distance travel, particularly flights crossing multiple climate zones. This equatorial bulge means that polar routes often provide even shorter distances than a perfect great circle route would suggest. For flights between major cities in the northern hemisphere like London to Tokyo or New York to Hong Kong, routing over or near the Arctic Circle can trim substantial miles from the journey. Airlines have perfected these calculations over decades, using sophisticated computer systems that factor in Earth's precise shape, saving passengers valuable time and reducing fuel consumption by thousands of gallons per flight, which translates to meaningful environmental benefits. Riding the invisible wind highways beyond the geometry of our planet, there exists an invisible network of atmospheric rivers that dramatically influences modern aviation. The jet streams, these powerful high-altitude wind currents, flowing primarily from west to east across the globe, can reach speeds exceeding 200 miles per hour during winter months, with some recordings showing speeds up to 300 knots in extreme conditions. Located at the boundary between the troposphere and stratosphere, 30 to 40,000 feet above Earth's surface, these natural highways can either accelerate aircraft dramatically or create significant headwinds that slow progress. Flight planners treat jet streams like moving roads in the sky, carefully routing eastbound flights to capture these powerful tailwinds while directing westbound flights to avoid bucking against them. The impact is remarkable. A transatlantic flight from New York to London typically takes about 90 minutes less than the return journey on identical aircraft. This is UNJ just about passenger convenience capturing favorable. Jet stream positions can reduce fuel consumption by up to 15% on long-haul flights, saving airlines millions of dollars annually while significantly reducing carbon emissions per passenger mile. Safety and weather in the equation. While efficiency drives much of route planning, safety considerations add layers of complexity that sometimes override the shortest path. Extended operations over remote oceans require special certification under regulations known as ETOPS, Extended Range Twin-Engine Operational Performance Standards, which ensure aircraft can reach suitable emergency landing sites within specified time frames. Modern twin-engine aircraft, like the Airbus A350, can now achieve ECOPS 370 ratings, allowing them to fly routes up to 370 minutes from the nearest suitable airport paths that were once restricted exclusively to four-engine planets, though they must still maintain proximity to airports capable of handling emergency landings. Weather patterns introduce daily variations to flight paths that would surprise most passengers. Severe thunderstorms can tower above 60,000 feet far, higher than commercial aircraft. Cruise pilots to navigate around these dangerous systems, even if it means adding miles to the journey. Clear air, turbulence, invisible to radar and often lurking near jet stream boundaries, presents particular challenges. This phenomenon has injured flight attendants and unbuckled passengers, which is why pilots constantly adjust routes based on real-time weather reports from aircraft ahead of them, creating an evolving network of optimal paths. A new perspective on our curved world. Understanding why planes fly the routes they do offers more than practical knowledge about aviation. It provides a profound shift in how we perceive our planet and our place upon it. Those seemingly inefficient paths that puzzled you on flight tracking apps represent humanity's adaptation to physical reality rather than the convenient fictions of flat maps. This realization invites us to question what other aspects of our world we might be misunderstanding because of how we choose to represent or visualize complex realities. The mathematics underlying these roots, great circle geometry, geodesics on oblate spheroids, fluid dynamics of atmospheric circulation, demonstrate how scientific principles directly shape our daily experiences. Every time you board an international flight, you're benefiting from centuries of mathematical discovery, decades of meteorological research, and real-time computational power that would have seemed miraculous to travelers just 50 years ago. These optimized paths save the aviation industry billions of dollars and millions of tons of fuel annually, making air travel more accessible while reducing its environmental footprint. Next time you track a long-distance flight and notice that curious path arcing, far from what seems obvious, you'll recognize the elegant solution. It represents a triumph of mathematics, physics, and engineering working together. If you found this journey through aviation geography fascinating, subscribe to Orphiq for more explorations that challenge how you see the world. We dive deep into the surprising science behind everyday phenomena, revealing the hidden logic that shapes our modern lives. Share your thoughts in the comments. Have you ever been confused by a flight path? What other everyday mysteries would you like us to unravel? Your curiosity drives our content, and we'd love to hear what puzzles you about the world around you.